Hello, my name is Adil, and I, along with Rita and Yusuf, will be talking about nanoscience and batteries. Today, we will be looking at revolutionary developments of a silicon solid-state battery from the University of California, San Diego, in collaboration with LG Energy Solution. First, let's take a look at a lithium-ion battery. The cathode is the positive electrode and where the oxidation reaction occurs during discharge. Within is a metal oxide that is very electronegative. Next, the anode, which is the negative electrode and where the reduction reaction occurs. The anode contains sheets of graphene, and in between these are intercalated highly reactive lithium atoms, as lithium is an alkali metal with one valence electron. Between the cathode and anode is the electrolyte. This is a lithium solvent that allows only lithium ions to pass. Within the electrolyte is a porous separator, which prevents physical contact and is a semi-permeable layer. Finally, there is the solid electrolyte interface, which is a layer between the graphene anode and electrolyte solution. It is a protective layer formed from the first few charge cycles that increases battery life for long-term charges. UCSD aims to address grid energy storage issues and create cheaper, safer batteries by replacing graphene with silicon and a solid-state electrolyte. Firstly, when lithium ions sit between graphene sheets, the most thermodynamically stable configuration is 1 lithium to every 6 carbon atoms. For silicon, this is 4 lithium to 1 silicon atom, which is a theoretical increase of 10 times more storage capacity. Secondly, silicon is the second most abundant element within Earth's crust, making it more accessible and cheaper. UCSD has also addressed two key drawbacks that silicon has had. Silicon expands to approximately 400% when with lithium, which along with reactions between the solid electrolyte interface and silicon cause quick degradation. UCSD has opted to use microsilicon as it is able to tolerate volumetric expansion and a solid-state electrolyte to avoid premature degradation.
Researchers formed a stable and passivating solid electrolyte interface layer by using solid-state electrolytes instead of liquid electrolytes in an all-solid-state battery. They have incorporated a 99.9 weight% microsilicon electrode, using it in micro-Si, SSE, lithium nickel cobalt manganese oxide, NCM811 cells to enhance the interfacial stability. Researchers removed all carbon binders from the silicon anode, since carbon is known to reduce the stability of sulfide solid-state electrolytes, promoting its decomposition. Researchers analyzed the effects of eliminating carbon in the silicon anode and the passivating quality of the Si-SSE interface. They prepared the samples using two composite Si-SSE anodes that were either with 20 weight% carbon additives or without. Figure 2a illustrates the voltage profiles of both cells during the first lithiation. The results have shown that the carbon-free cell has an initial voltage plateau around 3.5 volts. However, the cell with 20 weight% carbon shows a significant decrease, with a lower initial voltage plateau at 2.5 volts, thus revealing the extensive carbon-induced decomposition of the SSE due to the 1-volt decrease in lithiation potential. It's more preferable to eliminate carbon entirely in microsilicon ASSB system since there are less capacity losses. Another experiment was performed using X-ray photoelectron spectroscopy, indicating that the presence of carbon results in the formation of nanocrystalline lithium sulfide, which is a major decomposition product. As such, carbon-free electrodes would substantially reduce SSE decomposition, leading to greater first-cycle Coulombic efficiency. Also, room temperature is the ideal condition for ASSB charge and discharge. Researchers analyzed the cycle life by maintaining a current density of 5 milliamps per centimeter squared at room temperature as shown in Figure 5D. They found that micro-Si and CM811 cells deliver a capacity retention of 80% after 500 cycles. Overall, the electrochemical results have reaffirmed the significant effectiveness of sulfide SSEs with microsilicon anodes.
So it's clear that this technology demonstrates great promise. But where exactly do solid-state batteries stand in today's ecosystem? Well, to answer this question, it's important to know that the goal of this research is to replace the lithium-ion battery, which is currently the go-to battery of our generation. The advantages of solid-state silicon anode batteries could revolutionize the electric vehicle industry as a whole. To identify these advantages, let's first compare the two. The liquid electrolyte within lithium-ion batteries is the source of many of the issues of this battery. Most notably, it drastically increases weight, puts it at a risk of leakage, and also makes it very sensitive to temperature changes, leading to overall instability. For the same reason, the battery is flammable and potentially even explosive. As some of you may be familiar, there are no shortages of news reports covering anything from cell phones to airplanes catching fire due to battery issues. As for solid-state batteries, the solid electrolyte approach increases stability and is safer across a broader temperature range. Solid-state batteries also charge faster, are lighter, smaller in size, and have an overall higher energy density, as these batteries can hold up to 50% more energy than their lithium-ion counterparts, which is very useful for electric vehicles. And to seal the deal, doing away with the use of cobalt, liquid leaks, fires, and explosions will exponentially decrease the environmental impact and reduce the overall emission output of batteries while still retaining the lithium-ion battery's recyclability. Now let's take a look at some current applications of solid-state batteries. Solid-state batteries have been used in smaller devices like radio frequency identification and wearable devices like smartwatches. They have also been used in cardiac pacemakers, which if you don't know are medical devices that generate electrical impulses to help the heart pump blood, as you can see in the GIF to the right. Furthermore, the Japanese giant of the automobile industry, Toyota, has already made great strides in this field and showed off their all-solid-state prototype electric vehicle when advertising for the 2022 Tokyo Olympic Games. So what's next for solid-state batteries? Well, the potential market size of solid-state batteries is expected to grow and will reach over $6 billion by 2030. Toyota also plans to provide a car capable of retaining 90% battery performance over 30 years, while still being able to charge from 0 to full in just 10 minutes. Furthermore, the company Mercedes-Benz is currently in development of the e-Toro bus to run exclusively on solid-state cells. And the obvious benefits of increased charge cycles and power delivery make it a no-brainer that smartphones will get involved. In fact, Samsung expects to have prototype all-solid-state battery cells ready by 2025. So will it be out with the old and in with the new? Well, it may be too soon to say for certain, but what we have presented today makes apparent that the maybe not so trusty lithium-ion battery has some fierce competition ahead of it, and the future of energy storage seems solid. I appreciate everyone for listening to our presentation.